Okay, for section P1, what we're going to start out with is some vocabulary dealing with different types of numbers. Okay, the first type is a real number. Okay. Almost all the numbers that we've dealt with so far in math have been real numbers. In Algebra 2, we talked a little bit about imaginary numbers. We'll get to those later. But for the time being, a real number here is just defined to be any number that can be written as a decimal. Okay. All right. We have also some other subsets of real numbers. Okay. And the first one is what we call the natural numbers or the counting numbers. Okay. So numbers like 1, 2, 3, 4, 5, 6, you'll notice that in that pattern there's no fractions or decimals. Okay. There are also no zero and also no negatives. Okay. So if a number is a natural number that fits into that category, it cannot be a negative, cannot be zero, cannot be any kind of fraction or decimal. It's got to be just the positive counting or whole numbers. Okay. The whole numbers are numbers that are the same as the natural numbers, except we do add zero. So 0 is the only thing that's in addition to the naturals. So if we add 0 to it, then it becomes the set of whole numbers if we add 0 to it. Okay. And then finally, the next set is a set of integers, and that is going to be all the whole numbers in addition to their negatives. Okay? So any number that's both positive or negative, okay, but again is no fractions or decimals, okay, is going to qualify as an integer. Okay. Right, so again, 3 subsets so far. We'll be dealing with some more in just a few minutes. But, questions so far? Next, we're going to look at a set called the rational numbers. And the key issue on rational numbers is that we can represent any rational number with a ratio a over b, where a and b are integers. And we know that from our previous work that in a fraction of any sort, when we have a over b, that b cannot equal 0, because we can't have 0 on the bottom of a fraction. Okay. Right. And ultimately, again, a rational number, just the simplest terms, is that it's any number that can be written as a fraction. Okay. Now, one part of this that we're going to look at is this, what we call set builder notation. Okay. And there's a couple of key elements to the set builder notation that we're going to see throughout the book, etc. Is first of all that we have, notice that we have the braces around the outsides of the statement that we're given. Okay, and then the other key sign is this vertical line that's between this and this. These two parts are separated. Okay. All right, and what it boils down to is that when we have whatever expression over on this side, okay, we read this as, in our case, a over b. And depending on what expression we're dealing with, it's not always a over b. It could be whatever. We're going to see a bunch of them as we go. But the key element is, how do we read this sign in English? That little sign right there reads such that. Okay. So that vertical line reads such that. So we would read this sentence as, okay, anything is a rational number, okay, a over b, such that a and b are integers and b cannot equal 0. Okay, so like I said, in the set builder notation, that's probably the key that you need to make sure you see, that is that what that symbol means, and that symbol means such that. That's the way that's read in English. Okay. Okay. We discussed when we did our opener, when we do a division, when we're dealing with a rational number, whether it be one like we had before where the bigger number would be on top and the smaller number would be on bottom, or if we had something like 1/5 where the smaller number is on top and the bigger one's on the bottom. Okay. Any rational number, okay, can be written in decimal form, and one thing that's always going to happen is it's either going to terminate or it's going to repeat. So when we do any division of two integers, we're either going to get something that repeats or something that terminates. Okay, those are the only two options. Okay. Now, just to illustrate that point, if we do take a rational number like, say, negative 37 over 9, okay, and we're asked to change it to decimal form, and like I said, this is why we opened up with the problem that we did today, because if we're going to be asked to do this division, and we need to come up with an answer for this, okay, and we write it in the long division notation. Okay, we can see that 9 does not go into 3, but it does go into 37 4 times. And if we subtract, we get 1. Now, ultimately, in this case, though, we're asked to write it as a decimal, so this is going to be where we don't write the remainder part. We're going to, ultimately, if it's not a 0 remainder, if it doesn't go in there whole, then we're going to have to add some zeros here. And one of the questions is how many zeros am I going to need to add? Well, we don't really know right off the bat. Okay, we just add a few there. We might not even need the 3 that I did, or we might need more than 3. Because ultimately we have to keep carrying this division process out until it repeats or terminates. Okay, one of those two things has to happen. So let's go ahead and carry on here. If we bring down our 0, we have 10, which we know that's going to be a 1. And if we subtract, we're going to get 1. Bring down our 0, we get 10 again. Well, it would be 1 again then, 9. And if we start to see the pattern, is this ever going to change if we keep bringing down zeros? No. So like I said, how many zeros do we need to add? Well, depends on how long it takes to either find what the repeating part is or when it terminates. So if I'm going to write this as a final answer, then my answer would be 4.1 repeating, which we know is the horizontal bar above. And remember, the other issue here is that we started off with a negative 37 over 9, so the answer is actually negative 4.1 repeating. Questions so far in that process? And of course, this can be done with a problem like, say, 6/25, if you will, where the fraction is not improper. Got a smaller number on top. And if we do that, we can see right away that 25 does not go into 6. So we have to start making zeros and a decimal point. Again, how many? Don't know when we start off right off the bat. So 25 we do know can go into 60 twice. That would get us to 50. And if we subtract 60 and 50, we get 10. Bring down a 0, we get 100. Which of course 25 goes into 100 4 times. And in this case we get a 0 remainder. So if we get a 0 remainder, once again, we're done. Okay, so this one actually terminates. And so the final answer then would just be simply 0.24. So again, the negative 37/9 and the 6/25 are examples of rational numbers. Okay, and again, rational numbers can always be written as decimal numbers. And once again, they're either going to repeat or terminate. Okay. Questions so far? Right. Now, the other another type of real number is an irrational number, and this tricky definition: if a number is irrational, if it's not rational. Okay, but ultimately, the best way to tell whether we have an irrational number or not is by this decimal idea. Okay, if we have a number that can be written as a fraction, it's automatically rational. Okay, we can write it as a decimal by doing the division. Okay. But there are some numbers that are irrational, and ultimately the key is that the decimal form of an irrational number is infinitely non-repeating. Okay? So an irrational number does not repeat, also does not terminate. Okay, you might want to add that too. So it does not repeat, does not terminate. And we'll give a couple of examples here. Can anybody think of an example of a number that we might know that does not repeat or terminate? Pi. Yeah, pi would be a great example. So pi. Okay. If I think of another example of a number we worked with in the past that's an irrational number, does not repeat or terminate, if we look at the decimal for it. Yep. E is another one. We'll be dealing with that quite a bit in this class again. So those are two famous ones. Infinity is not a number essentially, so that would not qualify. Good guess though. You might think of another type of number that we've dealt with that doesn't have a repeating or terminating decimal. How about the square root of 3? If you punch that in your calculator, the decimal, again, does not repeat or terminate. Any square roots that are not perfect squares, square root of 9 obviously doesn't count because that's 3, it terminates. Okay, but if we have the square root of 3 or 5 or 7 or some number that's not a perfect square, if you look at the decimal for it, it does not repeat, does not terminate. Okay. Questions so far? All right, a couple more things we're going to look at, and then we're going to practice a little bit. Real number line. We have, of course, positive numbers, negative numbers on the number line. Okay. Irrational numbers can also be part of a number line. Okay. Ultimately, if we're going to place them on the number line, though, it's going to have to be an estimate. Okay. If we have something that's exact, we could put it in its proper spot, especially if it were a whole number or an integer, something negative or positive that actually falls on the tick mark. Okay. Again, if we're going to graph any kind of number on a number line, we're ultimately estimating. If I had 2.5, that would still be an estimate. I would just put it roughly in the middle. Okay. And what we're going to look at next is some inequality symbols. Okay. Because we're essentially going to graph some solution sets on a number line, and we're going to need to make sure we recognize the inequality symbols. Okay. And we have on the left side the symbols. A greater than B is the way that's read, of course. If we have the arrow pointing to the left, if you will, and we read from left to right, we would say A is less than B. When we have a line under that, we remember that that's greater than or equal to, and also less than or equal to. And again, we call these inequality symbols. Okay. So hopefully much of this is already known by us, since we've already aced Algebra 2. Okay. And we do have one property that's probably not familiar by name to us. Okay. But I do want to point out this property, this trichotomy property. If we have any two real numbers, then exactly one of the following is true. Okay. Either A is less than B, A is equal to B, or A is greater than B. Which seems really kind to us if we just looked at a glance, like, yeah, that makes common sense, doesn't it? Okay. But it is an actual mathematical property that one of those two things would be true if we have two numbers that are both real. Okay. One of those three things has to be true. Okay. Right. And what we're going to get into next here is dealing with inequalities. Okay, talking about either describing or graphing inequalities. When we have the inequality symbols, this is what we call inequality notation. Okay. If we were to describe this, okay, we would use words. So if we were asked to describe this set, what is this showing? Okay, this is showing numbers. Okay, x, of course, is a variable. We're showing numbers that are between -3 and 5. And keep in mind that since there's a or equal to symbol on this one, that means that we're including -3. So if we had to describe some numbers that would be in this set, -3 would be in the set. Okay, 0 would be in the set because that's between -3 and 5. Okay, 6 would not be in the set because it's not between -3 and 5, so on. So if we had to describe it with words, we would say it's all the numbers that are between -3 and 5, including -3. All right, and then the other part we're going to look at here is graphing the interval. So when we make our number line here, if we call that 0, and we go 1, 2, 3, 1, 2, 3, 4, 5. There's a couple of different ways that we can express this in a graph. Okay, the first way is we can use our bracket and parenthesis notation. And so at -3, which is this spot, what we want to make is a bracket, and at 5 we'd make a parenthesis. Okay, the bracket indicates that it's including, the parenthesis indicates that it's not including. Okay? And then between those two, we would draw a line connecting those two. Okay. So that would be one way to graph that particular interval. Another way is we could use the circle notation. And so if we have 0, 1, 2, 3, 1, 2, 3, 4, 5, at 5 and negative 3, once again. If we did an open circle at 5 and a closed circle at negative 3, that would represent the two symbols. Okay, closed circle goes with or equal to. Open circle goes with not or equal to. And once again, we could just connect those two. And that would be a graph that's showing that same solution set. Okay, all the numbers that are between negative 3 and 5, okay, where negative 3 is included. Questions on either of those two types of notation? So with that said, I do want to look at another vocabulary word here. This particular one that we've been dealing with is what we call a double inequality. And they've said it in words just like we said. It represents all the real numbers between negative 3 and 5, including negative 3, but remember excluding 5, because 5 is not part of the set if it's a less than sign. Okay. All right, and ultimately, I have a table here that has the three different notations that we're going to be using in this book quite often. Okay. The inequality notation we're probably the most familiar with. If we look at this one right here in the third line down, that's same as what we just had a minute ago. It's got the less than or equal to and the less than on this side. And of course, these are just the different combinations that we could possibly have. And as we discussed earlier, the graphs that go along with those, okay, have in this particular case have bracket on both sides because they're both or equal to. Okay, and whoever typed this typed it wrong because these two should be what? Parentheses. Those two should be parentheses. So we'll fix that for them. Okay. And on this side we have bracket and parentheses, and on this side we have parentheses and bracket. And again, always brackets go with or equal to's. Okay, parentheses go with not or equal to's. Now, one of the things that we will often do from here on out in math is instead of drawing a graph, okay, or using inequality notation, there's a more compact notation called interval notation. Okay. And with interval notation, you notice that we have the same symbols. The brackets go along with the or equal to's. The parentheses go along with the not or equal to's. Okay, and so for our example, we had negative 3 less than or equal to x less than 5. Okay, the more compact way to write that without having to write the inequality symbols is just simply write negative 3 comma 5. And we got to be careful because it kind of looks like a point, okay, from what we're used to. But when we give a solution in interval notation, okay, we just write it in this manner, and ultimately that means the same thing as this. It means all the numbers between negative 3 and 5. Okay, and like I said, from here on out, and not only in pre-calc but in calculus, okay, in calculus we use nothing but interval notation. Okay, we rarely would ever write inequalities ever. Okay. So with that said, make sure that we see this is probably the most important part that we've done today is making sure that we start using this interval notation, okay, instead of this notation or drawing a graph. Okay. Questions so far? Okay. Like I said, in a couple minutes we're going to have a chance to practice that. Okay. And just one more table here. Instead of having a double inequality, you'll notice that in this case we just have single inequalities, if you will. So we just, in this case, showing all the numbers that are greater than or equal to some a, whatever a might be. Okay, and you'll notice that on the graph part, same idea here with or equal to's. Or equal to's get brackets, nons get parentheses. Same in interval notation. If I want to show all the numbers that are bigger than some particular number, it's going to look like this. It's going to go from whatever that small number is, whatever it may be, to infinity. And one thing I want you to notice about the infinities here, what do the infinities all have next to them? Parentheses or brackets? Parentheses. Remember why? Brackets indicate that we actually get to that number. Okay, can we ever actually get to infinity? No. So therefore infinities always get parentheses, never brackets. Okay. All right. Okay.